It can be quite correctly argued that life exists on Earth because of the abundant liquid water. Some of our nearby planets, like Venus and Mars, have water, but not necessarily as a liquid. Living things are mostly made of water. Think of what you need to survive, really just survive. Food, water, air. Well, naturally, I'm going to concentrate on water here. Water is of major importance to all living things. In some organisms, up to 90% of their body weight comes from water. Up to 60% of the adult human body is water. If you look at an average living thing, the mass of an object, 65% of that organism is oxygen. But most of the atoms, 9.5%, are hydrogen. Now keep in mind there's 2 hydrogens for every 1 oxygen in water. The brain and heart are composed of 73% water. The lungs are about 83%. The skin contains 64%. Muscles and kidneys are 79%. And even the bones of your body have water, 31%. Each day, humans must consume a certain amount of water to survive. Of course, this varies according to age and gender and where you live. But we are mostly water. Our chemistry is aqueous. So the chemical nature of water is one that we must examine, as it is true for all living things. Water is the only known substance to exist as a solid, liquid, and a gas naturally. As water is boiled, kinetic energy causes the hydrogen bonds to break completely and allows water molecules to escape into the air as gas, steam, or water vapor. When water freezes, water molecules form a crystalline structure maintained by hydrogen bonding. Solid water or ice is less dense than liquid water. Ice is less dense because the orientation of hydrogen bonds causes molecules to push further apart, which lowers its density. For other liquids, solidification when the temperature drops, including the lowering of kinetic energy, which allows the molecule to more tightly pack, makes a solid denser than its liquid form. Because ice is less dense than water, it's able to float at the surface of water, and that's really important to life. In lakes and ponds, ice forms on the surface of the water, creating an insulating barrier that protects the animals and plant life in the pond from freezing. Without this layer of insulating ice, plants and animals living in the pond would freeze in the solid block of ice and could not survive. Keep in mind, in the past there have been extreme ice ages where the entire planet froze in what's called a snowball Earth. If water froze from the bottom up, life would no longer be here. Water is covalently bonded, but it's a polar covalent bond. The electrons are not shared equally. It means that while water molecules are neutral as a whole, one end of the water molecule tends to have a positive charge, while the other has a negative. The oxygen has a slight negative, while the hydrogen has a slight positive. Each end of the water is attracted to the opposite charged end of another water molecule. That it allows it to create hydrogen bonds. Water's polarity is responsible for the stickiness or cohesion between molecules and many of its properties. Water is sticky because of the way that it bonds. No, I don't mean sticky like glue, but water sticks to water in a process called cohesion, and it sticks to other things in a process called adhesion. Adhesion and cohesion are properties that affect every water molecule on Earth, as well as how they interact with every other substance. Water is highly cohesive. It is the highest of the non-metallic liquids. Water is sticky and clumps together into drops because of cohesive properties, but chemistry and electricity are involved at a more detailed level. If you've ever played with a bar magnet, and you know that positive repels positive and negative repels negative, but positive attracts negative. Cohesion allows for the development of surface tension, which allows substances to withstand being ruptured when placed under tension or stress, or allowing the insect to walk on water, or that bubble of water that forms at the top of the glass when you just slightly overfill it. Adhesion is a little different. It's when molecules of water are attracted to other types of molecules, and this attraction is sometimes stronger than water's cohesive forces, especially when you're exposed to charged surfaces. When water climbs up the tube placed in a glass of water, or you put water in a graduated cylinder, you can see the meniscus. The water molecules are attracted to the charged glass walls of the capillary more than they are to each other. But capillary action doesn't have to be glass. When you put the edge of a towel into some liquid and it soaks up the liquid, that's adhesion at work. One real life example of how cohesive and adhesive forces are important for life, when you're looking at a plant, they don't have a heart to pump their fluids throughout their system. What they rely on is a combination of evaporation and adhesion and cohesion. It's called evapotranspiration. The forces of adhesion and cohesion create a pull on the water column. The water in the roots down here is pulled up the plant through adhesion and cohesion, and then out the stoma, or the openings in the leaves of the plant. As the water evaporates out of the leaf, more water is pulled from the roots, and the plant is able to get the water that it needs. And it all comes back to adhesion and cohesion. Water, which not only dissolves many compounds but also dissolves more substances than any other liquid, is considered the universal solvent. Is it actually a universal solvent? No, but it's a very, very good solvent. It's polar, which means that it's able to dissolve other polar things because like dissolves like. Hydrophilic molecules, like ionic molecules, will dissolve easily in water. Because water is partially positive and partially negative, it forms a hydration shell around the ions, disassociating them, separating them. The hydrogens are positively charged, so they will be attracted to the negative chlorines. The oxygens are negatively charged, so they'll be associated with the positive sodiums. So hydrophilic things will dissolve easily in water. But not all molecules in biology are polar. Some are nonpolar. These are considered hydrophobic, or at least non-ionic, covalent, something, where they are going to be very hard for water to break down. What actually ends up happening is that water changes its hydrogen bonding patterns around the hydrophobic molecule, producing a cage-like structure. This change actually alters the entropy. It makes it decrease, making it more ordered than in liquid water, so the molecule will not dissolve. When heat is absorbed by water, hydrogen bonds are broken and water molecules can move freely. When the temperature of water decreases, the hydrogen bonds are formed and release a considerable amount of energy. So because of this, water has a very high specific heat, and it actually has the highest specific heat capacity of any liquid. Specific heat is defined as the amount of heat 1 gram of substance must absorb or lose to change its temperature by 1 degree Celsius. For water, this amount is 1 calorie, or 4.184 joules. As a result, it takes water a long time to heat up and a long time to cool down. In fact, the specific heat capacity of water is about 5 times more than that of sand. This explains why the land cools faster than the sea and why water helps to moderate the climate. Resistance to sudden temperature change makes water an excellent habitat, allowing organisms to survive without experiencing wide temperature fluctuation. Many organisms are mainly composed of water, so that high heat capacity allows highly regulated internal body temperature. For example, the temperature of your body does not drastically drop to the same temperature as the outside temperature while you are skiing or playing in the snow. Due to its high heat capacity, water is used by so-called warm-blooded animals to more evenly disperse heat in their bodies, acting like the car's cooling system, transporting heat from warm places to cold places, causing the body to maintain a more even temperature. The pH scale you're used to seeing is based off of water. As we can see here, neutral chemicals are pH of 7. Distilled water is neutral. If you are less than 7, you are an acid. If you are greater than 7, you are a base. But in the end, it's entirely based off of water. Hydrogen ions are spontaneously generated in pure water by the dissociation of a small percentage of water molecules into equal numbers of H plus ions, hydrogen ions, and hydroxide, OH minus ions. The H plus is just a naked proton, and it's immediately attracted to unionized water molecules, so you will see it as hydronium, or H3O plus. But that's not all pH is. If you actually look at pH, if you take the concentration of H plus and the concentration of OH minus, it's going to yield a 10 to the negative 14th concentration. Please remember that if your mantissa is exactly 1, you do not have to write it. So what this is really saying is that the concentration is 1.0 times 10 to the negative 14th. But acids dissociate into H+, so if you look at the concentration of H+, and use pH formula, negative log of H+ will give me my pH. So say for example I have an H+ concentration of 10 to the negative 4, knowing what a log is, my pH is 4. If I'm looking at my other molecules, my H's and my OH's, if I have that, I know if it's a 0 to a 6, it's an acid. If it's a 7 to a 14, it is a base. And that is very important to living things. It's in logarithmic scale, so each number change is a times 10 change. So if I go from a pH of 3 to a pH of 5, my molecule is 10 times 10, so 100 times more basic than it was. But how can organisms whose bodies require a near neutral pH ingest acidic and basic substances, like drinking orange juice? Buffers are the key here. Buffers consist of a weak acid and its conjugate base, and enables them to absorb excess H plus or OH minus, keeping the system's pH within a narrow range and keeping you alive.